Welcome to KCC Diesel Online. My name is Jeff Rush, and this is DST 110H, Fundamentals of Electricity. Today's learning objectives are relating electrical terms including voltage, current, and resistance to their hydraulic or pneumatic counterpart. Now, I may not refer to hydraulics and pneumatics much in this course. I don't really like to relate these two together. Sometimes the comparison isn't seamless, tends to confuse people. They assume that you know hydraulics or pneumatics before you start this, and I don't know why they do that. Some people understand those concepts a little better. If you get it, great. If you don't, move on. Don't spend too much time trying to figure that out. We teach hydraulics in the class later. Pneumatics and hydraulics have a lot in common. We'll talk about those things as we move on. A lot of people find that electrical helps them learn hydraulic later when we do hydraulics later, things like that, but we'll talk about those relationships. Explain the relationship among voltage, current, resistance in an electrical circuit. And then apply Ohm's law to simple electrical circuits to determine the unknown voltage, current, or resistance. So Ohm's law is a great tool for figuring out voltage totals, current totals, resistance totals, things like that. Believe it or not, this is one of those times where you are going to use just a small algebraic equation to solve for something. It's very simple. It's nothing to be scared of. You'll be surprised how easy it is in the end. We're going to perform measurements of voltage, current, resistance, using a digital multimeter, so a DMM. A digital multimeter is a bunch of different meters put into one. Now, if you've been in the industry as long as I have, you probably remember at your college or something like that, that they had a voltmeter, an ohm meter, a amp meter. Well, these are all of those put together into 1 meter, and they call it a digital multimeter. Okay? We're going to describe the concept of a voltage drop across a resistance when current flows through the resistance. So, voltage is essentially used up as it goes through a circuit, and that's what we're going to talk about. We're going to demonstrate Kirchhoff's voltage and current law through voltage and current measurements obtained from a series circuit, a parallel circuit, and a series parallel circuit. So just as we have other physical laws, other principles, we have laws in electricity, we have laws of physics that apply to electricity that we are going to learn to harness and learn to understand in DST 110H. Determine the total circuit resistance in a series parallel electrical circuit given the individual resistor values. We're not going to go into this a lot right now. We're going to brush over it because you really need to have an understanding of the physical properties before we get into this a great deal. So I'm going to brush across this. Just know that if you don't understand it right now, you will by the end. This class is very secular. We're going to come back to things over and over and over until you get them. We will try in our 7 terms here at KCC Diesel, or Auto, to actually master these. Okay. But we're just introducing the concepts. Don't feel like if today you don't get it, that tomorrow you won't get it, or the next day you won't get it. Eventually you will get it. We're dedicated to helping you understand it by the time you leave school here. And everything that we do here at KCC in the automotive and diesel departments are completely surrounded by electricity. So you will get a lot of electrical experience by the time you finish up here. All right, so let's talk about the fundamentals of electricity. Atoms, protons, electrons, and of course we like to say croutons because that's funny. But if you ever have a conversation with somebody and you use the word croutons and they don't understand, then they really have no understanding of electricity, and you should probably either educate them or walk away quickly because that conversation could go downhill very quickly. All right, atoms are the smallest pieces of any known element. Atoms are made up of protons, electrons, and neutrons. Protons have a positive charge, and electrons have a negative charge. So if you just remember positive, electrons, negative. If you can't remember the electrons because it's not a negatron or something like that, just remember that protons have the positive charge and the electrons have the negative. And then obviously neutrons are neutral, so we don't have to worry about that one. Like charges repel and opposites. Like charges repel and opposite charges attract. Okay, so just like your magnet, that is basically how the electrons and protons work. They are attracted to each other. They keep themselves in orbit. So unlike charges, the positive and the negative, they're going to attract, just like ends of a magnet. Okay? Like charges are going to repel, same thing, just like the magnet. I think we've all played with magnets as a kid. If not, we will play with magnets a little bit if you'd like in the lab. So if you haven't played with a magnet, you can either go get a magnet to play with or you can wait till lab and we'll discuss it. So like charges repel. I don't know how many of you guys are interested in like roller coaster technology and things like that, but we're actually harnessing this technology within some of our inventions like roller coasters to propel or slow down the roller coaster. So some neat technology as far as that goes. All right, atoms, protons, and electrons. Again, atoms are like a solar system. Protons are the sun, and with electrons orbiting like planets. Okay, so again, here is our electrons floating around our protons. Okay, they are on the outside, and this is actually a copper atom, and we'll talk about these different rings and valences and what they mean. All right, displacing electrons. So, like I said, the electrons are on the outside of the atom, and rubbing two dissimilar materials can strip electrons from one material and add them to another. One material has a positive charge, it's missing electrons, and one material has a negative charge, too many electrons. And an atom with unequal numbers of protons and electrons is called an ion. So, positively charged ions, negatively charged ions, we'll talk about that. They will exchange electrons. They will displace electrons. Displacing electrons. A material with an excess of electrons or protons will attract a material with the opposite charge. An atom with more protons than electrons is a positive ion. An atom with more electrons than protons is a negative ion. Okay. So here's how we're getting those like charges and dislike charges, and we'll start to talk about this. Electrons flow from a location where there is extra electrons to a location that is missing electrons, and so we'll talk about that. Okay, so your plastic comb with a negative charge after combing your hair. And we're talking about rubbing it in your hair and basically making it a negative charge and picking up pieces of paper because the pieces of paper have a positive charge. So the opposites attract. Okay, so if you haven't done this, you can do this at home. Same thing with rubbing a balloon on your head and then making it stick to the wall. Okay. We are upsetting the balance between those, and we are making one positive and one negative so that they will attract each other. All right, electrical potential exists between two materials, one with an excess of electrons, which is a negative charge, and one with an absence of electrons, which is a positive charge. Okay, so there has to be an electric potential between the two. Okay. Electrical potential is known as voltage or electromotive force. So we call this EMF. Okay? Not electromagnetic force, that's a different thing, but we're going to use that three-letter abbreviation kind of in a couple of different ways. So electromotive force. Okay? Voltage can be thought of as a pressure in an electrical circuit. Okay? So we're going to talk about that. So the voltage is the amount of pressure. So like PSI of air pressure. Okay? The unit of measurement of voltage or EMF is the volt. Okay? So we measure voltage in volts, I should say. The symbol for voltage is the V. So the truck battery voltage is usually called 12V, 12 volts. Okay? You can't have 24 volts, you can't have 36 volts, and upwards and onwards from there. But most of our automotive and trucks are using 12 volt batteries. The flow of electricity is known as electric current. Okay, so now I want you to listen to that. The flow of electricity is known as current. Okay, so think of water flowing. Water has a current, right? Because it's flowing. Okay, so this is where we're going to use a little bit of a hydraulic metaphor here. I want you to think of your water sitting behind the tap at home. So the valve is closed and you have water pressure. Okay? That pressure is like the voltage in a battery. Okay? That battery has pressure. Okay? Now when we open up the spigot, it's just like trying to turn on the headlight switch. When we turn on the spigot and the water comes out, we turn on the valve and the water comes out, we now have flow. So current is flowing. Water current is flowing out of the faucet. When we turn on the headlamp switch, okay, electrical current is flowing out of the battery to the headlamps, making them light up. That current has a certain amount of pressure. Let's go back to the water. That water has a certain amount of pressure, okay, based on pipes, based on, how high the water is up at the water tower, how strong the pump is at the pumping station. If you have a well, how strong your well pump is. That's how that works, okay? So voltage is pressure. Voltage doesn't flow, okay? Just like water pressure. Water pressure is the pressure. It's a measurement of pressure. It's a measurement of potential. It is not, we aren't going to flow volts. No volts are flowing. Current is flowing. Current is flowing at a certain pressure. We measure that pressure in volts. Okay. Now, the reason I'm trying to pound that in is that this is a concept that people get messed up with. Now, if you get this from the very beginning, we measure electrical pressure in volts. We measure electrical current. Okay. We measure that in amps. So current is measured in amps. Okay? Now look here. Watch my little arrow. Current is measured in amps. The symbol for amps is the A. Okay? So the symbol for volts is the V. Okay, the direction of current flow. A battery has two terminals, positive and negative. The positive terminal is marked with a plus and the negative is marked with a minus sign. Conventional theory is that the electricity will flow from positive to negative. Okay? That is the way we will talk about it 99.9% of the time in automotive and diesel. Now then there's electron theory. And an electron theory is a little bit more scientifically correct. It states that things move from the negative to the positive. And as you see in our theory, we talked about the negative atoms, the electrons, the negative electrons in your atom will move to the positive. Okay? And that's how we see it, from negative to positive. That's technically correct. That is absolutely correct. However, that isn't how we will be discussing it most of the time. Most of the time we will be talking about conventional theory. and you'll see why this works out better. But we do want to talk about both because they are both very relevant. All right, so if you look here in your book at this cars analogy, so here are our cars at the stop sign. In order for this car, when this car goes, it creates a space, okay? And when the next car lines up, the space is what's moving, okay? You see the space moving back, it's moving back, it's moving back. That's how electron flow is like the movement of cars, while the conventional flow is like the movement of spaces to the left. Both are correct, but when we talk about electrical, how our schematics are set up, when we read diagrams, it's all going to be in conventional flow. So don't worry too much about electron theory. It's not very important. We're not going to worry about it. All right, direct and alternating current. So let's talk about this. Almost everything on a truck or a car uses direct current, DC. So we'll talk a little bit about this. Direct current does not change direction or amplitude. And let's go ahead and we'll talk about this here in a second a little bit more. Alternating current changes amplitudes and direction of flow continually. So let's see. Okay, so now I've drawn down here at the bottom a description of DC and AC. So DC voltage, it never changes direction, okay? So as the current flows, the 12 volts just kind of stays steady, and I know this is kind of a weird drawing, but that's okay. So the red line here indicates that our voltage is staying right steady at 12 volts, okay? And it won't always stay perfectly steady, but now this is how 12 volts works. Now, 12 volts DC, I should say. Now, AC voltage, we are going to have 12 volts going up. We're going to have 12 volts coming down, 12 volts going up, 12 volts going down. So while it's on the top side of the line, these are positive peaks. Positive, positive, positive. These are negative peaks, negative, 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 negative. And that's basically how you look at that. There are positives and negatives to both types of system, pardon the pun. There are uses for both. So 12 volt DC, we use that in our cars. Okay, 12 volt AC, we don't really use a lot of 12 volt AC anywhere other than in our alternator. Okay, our alternator uses 12 volt DC. So our alternator produces 12 volts AC, and then we actually run it through a set of diodes and make it into 12 volts DC. Now, where you're going to see the alternating current most often in your world is going to be at home. You're going to see it looking more like this, and it's going to be 120 volts. Okay, 120 volts. Negative, positive. Now this is your wall socket. Okay, this is basically your power socket at home. You've got your little face here, right? And you've got your sockets, right? So you got your 120 here and your 120 here, and then you've got your ground socket. Okay, so that's what you are going to see most of the time in your world at home. You're going to see, that's what you're going to see most of the time. So other than that, I really wouldn't worry about it too much. We'll get into these concepts a lot more as we move along. Excuse me. Conductors are made of materials that allow electron flow with a little opposition. So let's talk about conductors. Many of you are probably thinking of a good conductor. You might be thinking of something that isn't a good conductor. One of the things that we use the most in automotive is copper. So copper is a great conductor. We use a lot of copper wires to conduct electricity from one place to another. Conductors on a truck are usually made of copper. Free electrons are easily dislodged from the outermost band of an atom and into the next, into the outer band of the atom next to it. The outermost band of an atom is called the valence band. Okay, this valence band is very important. Atoms with one or two electrons in the valence make good conductors. So we want to see electrons on the outer valence of the atom, and that means it's a good conductor of electricity. So I said that could be a good conductor of electricity. Can it be a good conductor of other things like heat? Yeah, so copper is a great conductor of heat as well. So electrical current and temperature and heat have a lot in common, and there's definitely a relationship between heat and conductivity when it comes to electricity and electrical circuits. All right, so here's another. Electron flow is like marbles in a tube. A marble that enters the tube on the left is not the same marble that exits on the from the tube on the right. So we put a marble in here and a different marble comes out over here, right? So this is basically what's happening is an electron moves and it moves to the next one, 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 moves, and then out pops a different electron or out pops a different marble. And that is how electricity really is flowing. All right, electrical flow or electron flow is described to be an energy wave that flows through a conductor. The energy wave travels near the speed of light. Okay, so we talk a lot about this when we talk about electricity, how fast things happen. And it's near the speed of light. So when we talk about electrical circuits and things like that, that's the speed you're talking about. You're talking about that kind of speed. The actual electrons flow a few inches per hour. Okay? The energy wave is similar to the energy wave produced in a pool cue that strikes on a line of closely lined up pool balls. Only the last ball rolls. So we can see this in the Da Vinci balls or whatever. As you strike the ball, it's the wave of energy that moves the last ball on the other end. That's what we're talking about. So the fact that the electrons only flow a few inches per hour is pretty crazy. When we think about how much flow we have, now obviously that's going to be relative to how much current we're flowing and things like that. But that's what you're talking about when you're talking about like headlights and things like that. One electron starts at one end and only moves a few inches per hour because we're talking about very, 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 very small amounts of space. All right, resistance. Resistance is the opposition to flow of the electric current. So let's talk about this. We'll go back to our water spigot analogy. That valve that stops the water flow, that's resistance. That valve, when we close that valve, it's closing the end of the spigot. That is very high resistance, right? That's what's creating the resistance to flow for the water. Resistance in a circuit is much the same way. An open switch, okay? An open switch, and let me talk about that. When I talk about open switches, I'm talking about talking about a switch that looks something like this. And we'll put a little dot on the end. And that switch is open. Okay? We'll talk about that. So that's an open switch. Now, when we close that switch, it will look like this. Okay? There. And that's our closed switch. And let me make sure that actually does close. There we go. That closed switch is very important because right here we have a lot of resistance. Okay, here we have almost no resistance, and that's going to allow current to flow through that circuit. Resistance is the opposition to flow of electrical current. Ohms is the unit of measurement of electrical resistance. The symbol for the ohms, or for ohms, is the Greek letter omega. So we will be writing this symbol quite often, so get used to it, start practicing now. Resistors are electrical components with a specific value of resistance. All right, so let's talk a little bit about this. So in order to have pressure, we have to have resistance. Okay, so I want you to think of a bucket of water. When we pour that water out, there's really no pressure to it, right? There's a lot of flow, but no pressure. Now, when we run it through a hose, you turn the hose on and you see it coming, pouring out of the nozzle. It'll make a gentle arc, okay? Now we stick our thumb over the end of that hose and it sprays. The water has some velocity to it now, and it will go some distance. That's the same way an electrical circuit works, very much the same way. Obviously now if we come up here to our open circuit, our voltage can only flow to right here, and then you would need a lot of pressure, way more than 12 volts, to jump from here to here. So not much is gonna make that happen. You're gonna have to have a lot more volts to jump that gap, kind of like a spark plug does. Okay, so you aren't gonna have that right away. And so that's basically an open circuit, just like closing the valve on your water spigot. Okay. Now, when you have low resistance, water is going to flow, or electrical current in this case is going to flow through that circuit like that. That's the difference. Okay. And you see. An open circuit is a circuit that will not flow. An open valve, however, when we open the valve, water flows, right? So that's where that analogy breaks down. That's where that metaphor breaks down. So an open circuit is a circuit not flowing current. A closed circuit is a circuit that is flowing current. Okay, and we'll talk more about resistance. So wire resistance. All the electrical conductors have some resistance, even though it may be a small amount. So we have different sizes of wires and things like that, and the resistance is going to change depending on the size of the wire or cable. Wire resistance increases with the length of the wire. So a 10 millimeter wire has 10 times the resistance as a 1 millimeter wire. Okay, and now they're talking about length here, not gauge. We're talking about a 10 millimeter long wire has 10 times the resistance as a 1 millimeter wire. Okay, a tungsten filament in a light bulb uses resistance to heat up and light when the electrical current flows through it. Okay, so there's this relationship between electricity and heat and light, and we'll talk a little bit more about that. All right, so we have a very small diameter filament, but we said it was tungsten. Tungsten's very strong. So we make this very small. Now these large diameter conductors are going to conduct electricity through this conductor. And let me throw some color on this. So we always use black kind of as the negative. So this will be positive. So we're going to bring positive up here. Okay, positive is going to flow through the conductor, and then it's going to meet the negative over here. Okay, and then it's going to flow back to. So this was positive, this was negative. And in the meantime, it's going to heat up this element. This element here is going to heat up, and as it heats up, it's going to create light. Okay, so if we look at our situation here, we have voltage flowing through and back out, and then back down. So from the battery down here, it's flowing up. Okay, and it's going through, and we're creating heat and light. So there's only so many choices for electricity to change states. Now, you've probably heard that we don't really use up electricity, it changes. Energy never dies, it just changes shape. So in this case, the electricity from our bulb here is changing, okay, from chemical energy stored in this battery to heat and light energy going from this bulb, and then flows back to the battery. And I guess in this case, I really should have showed that it went from the positive through the bulb back to the negative. I just didn't notice. My bad. All right, an insulator. So you'll notice we don't have a lot of copper wires just hanging out there in our cars. There are maybe a couple of them, but for the most part, our wires are insulated. An insulator is a material that offers a great deal of resistance to flow of current. The resistance of an insulator is said to be very high. Insulators have 5 or more valence electrons. Okay, so on that outer valence, they have 5 or more valence electrons. Plastic, rubber, and glass are good examples of insulators. So, let's think of a few things. Our thermos in school, we used to all have old plastic thermoses, okay, in our lunch boxes, if you're that old to have a lunchbox. So that's plastic. Our plastic water bottles are insulated with plastic. Rubber, the bottom of your rubber shoe. The coating on our wires is more like rubber than it is like plastic, but it's a polymer of rubber and plastic basically, and it coats our wires so that we don't have uninsulated wires. And then I don't know how many of you guys remember that the old glass insulators on the top of old electrical lines and electrical poles. They were used to insulate the wires as they ran down the poles. All right, increasing the voltage causes the electrical current flowing through a fixed value of resistance to increase. So when we increase the voltage, we increase the current. Now that makes sense, right? When we increase the pressure, we increase the flow. Does that make sense? It does to me. So think of your garden hose again. If you were able to add a pump to your garden hose and added more pressure, you would pump out more water. Okay? And so for you farmers who use a lot of pumps and hydraulics, you probably understand that concept better than some of us city kids. Increasing the resistance while keeping the voltage source held at a fixed value causes the electrical current flowing through the resistance to decrease. So if everything is equal, being that the voltage is equal, and we increase resistance while keeping the voltage source held at a fixed value like 12 volts, this will cause the electrical current flowing through the resistance to decrease. So why is this important? Well, let's think about a couple of things. So let's think about this increasing the voltage. How many of you have ever driven an old car, an old truck, and when you revved up the engine, the headlights got brighter? They came on, they got brighter, and then when you brought the idle back down, they got kind of dim again. That's that same concept. With increased voltage, when you accelerated the engine, the generator or alternator moved faster, creating more voltage, and then more flow to the headlights, so we flowed more current and they got brighter. Increasing the resistance while keeping the voltage source held at a fixed value. That is an example of, how many of you guys have ever seen the rheostat or the dimmer on your dash? So you've got your bright dash lights, but yet you've got a knob or a thumb wheel, or sometimes even a plus and minus button on the dash, and you're increasing and decreasing the brightness of your gauges. That's what that's doing. Everything else is the same, voltage is the same, but we are increasing or decreasing the resistance and making the lights go dimmer or brighter, depending on the original setting, and that's the basic concept there. All right, so that's an explanation of Ohm's law. So voltage divided by resistance equals current. Voltage, 1 volt divided by 1 ohm equals 1 amp. So if you can't remember Ohm's law, remember this. 1 volt divided by 1 ohm equals 1 amp. E, being electromotive force, EMF, divided by R, being the resistance, equals 1. Now we use the the symbol I, and now that's intensity. I is for intensity, and we use that for amps. So E equals voltage, R equals resistance, I, or intensity, equals amperes. Now intensity, flow, high flow, intensity, that's where they're getting that from. So E over R times I. Okay, we'll talk a little bit about that. So let's look at this. So we have volts over amps times ohms. Okay, so again, let me grab my pen here. There is, let's see here. This is basically a divide. So anything underneath here, anything underneath this line, we're going to divide. And anything next to each other like this, we're going to multiply. So multiply and divide. All right, so as we're looking at this, we are going to see that they put a cover over this voltage. Now that means that we don't know what our voltage is. So if we're trying to find for voltage, we put our thumb over the voltage, and so if we know our amps and we know our ohms, we can find for volts. If we know our intensity or our resistance, we can find for E up here. Okay. Same goes for if we know our voltage and we know our resistance, we can find for our amperage or intensity. Same thing, amperage, intensity over here. So same thing, if we know our volts and our amps, or our E and our I, our electromotive force and our intensity, we can find for our resistance. We can find for our ohms. Okay? So Ohm's law, that's basically the memorization aid in a nutshell. These questions will be on the ASE. These questions will be on every test for electrical for quite a while until we're sure that you have memorized them. Electrical circuits are the path that the electrical current flows. Okay? These are their intended path. These are the road maps that we are going to lay out. The schematics are used to show the layout for the relationship of the electrical components. So schematics, like I said, are the map. Okay, they're the map. Now schematics, unlike a map where 1 inch equals 1 mile or 1 inch equals 10 miles, schematics are not drawn that way. So when you see a schematic, you can't assume that it means the distance. It's not calibrated that way or measured that way. Schematics are also known as circuit diagrams or wiring diagrams. Electrical schematics use symbols to indicate the electrical components found in the electrical circuit. So we use diagrams and component symbols to make up a wiring diagram. We'll talk a little bit more about that as we go along. Matter of fact, we'll talk a ton about it. So if you don't get it, we're going to come back to that 100 times. So common electrical symbols. So here's our battery. So here's our 1.5 volt battery that we were kind of dealing with earlier in that light bulb schematic. Here's what it's going to look like on our schematic. Here's a resistor. Okay, so we have that up and down voltage. Okay, here's a 2 ohm resistor. And a straight line like this may mean a wire. And so then if we put them all together, here's our 1.5 volt battery. That voltage is going to go up this wire, through the resistor, and back down to the negative. And that is our path. That's our circuit. And so we were able to read that. And we're going to continue to read schematics as we go through this program. All right, measuring pressure. So most pressure gauges display the difference between atmospheric pressure and the unknown pressure, and reads in PSIG. G equals gauge, so pounds per square inch. Gauge is how that reads. Some gauges display the difference between an absolute vacuum and the unknown pressure, and reads as a PSIA. Pounds per square inch absolute, A equals absolute. And a differential pressure gauge measures the difference between two different gauge ports. And so we'll talk a little bit about that. But that's measuring pressure in a hydraulic circuit or a fuel pump circuit, or possibly a pneumatic circuit. All right, measuring voltage. We already talked about measuring voltage. We measure voltage with volts. The unit of measure is volts. So we're still using our DMM, but we're using the voltmeter portion of our DMM and the electrical diagnostic tools that read voltage. Okay, voltmeters display the difference in electrical potential, which is voltage, between 2 points. The most common voltmeters are multimeters, or DMMs, digital multimeters, capable of reading volts, amps, and resistance. So we have one meter that is going to do it all. Test leads are wires with probes that connect the voltmeter to the circuit being tested. So we'll talk a little bit more about that. So here's what a typical voltmeter looks like. We have a dial gauge that's going to go from alternating volts to direct volts to direct millivolts, ohms. Then we have a diode tester, and then we get into milliamps, which is measuring flow, and then microamps. So we'll talk a little bit about that. The common port is for the black wire, and if we are measuring volts, we'll measure volt, ohms, and diode over here. For measuring amps, we've got to be into a couple of these sockets. Now there's some real precautionary tales, and so we'll talk a lot about this in lab, about what you can and can't do with the voltmeter. These meters are sensitive electronic pieces of equipment, so they have to be treated as such. You're going to buy your own multimeter and learn how to use it rather than burning up the school's meter. Measuring voltage continued. So test leads are typically colored red and black. The red leads are installed in the most positive point in the circuit. The black lead is installed in the most negative point in the circuit. We'll talk a little bit about that, how that works and where you're going to measure and why, and those types of things. Voltmeters are connected in a circuit in parallel. So we'll talk about parallel and series, and we'll get very used to that, but reference your book. All right, so here we are in parallel with the meter, and right here we are getting 12 volts. So what we're measuring is that we had 12 volts. We had basically 6 volts on this side and 6 volts on this side, and everything got dropped across the resistor. And we'll talk a little bit more about voltage drops and things like that. But this is how you test how this worked. Okay? All right, measuring current. Current flow through a circuit is measured with an ammeter. That ammeter, again, is going to be located most often in your digital multimeter. An ammeter is typically included in a multimeter. Going to talk about that. Ammeters are connected in series with the circuit, meaning it has to be part of the circuit. All of the electricity has to be flowing in and out of your multimeter. Most multimeters have a specific plug for reading the current. We'll talk a little bit about that in the lab. The circuit current cannot exceed a maximum amperage range. So multimeters, when you're measuring amperage, you can't measure the amperage of an alternator. You can't measure the amperage of a headlight typically. It's lower amperage that you're reading, so you have to be very careful with your meter. 10, 20 amps is about as much as you can read on a digital multimeter. If you need to read over that, then you need to get a different tool, and we'll talk about the appropriate tool for that. So as you can see here, we're measuring current with an ammeter, and we are part of the circuit. You notice the meter leads are in the circuit, okay, and that's very special. Okay, so you have to set up the meter right. So most often, what I find, people will say, "Hey, Mr. Rush, I don't have any voltage, or I don't have any current," and it's because they aren't hooked in to the circuit correctly. The switch isn't closed, so there's some different things. Now, obviously, if we're measuring current, we need to have voltage flowing. There can't be an open circuit anywhere, things like that. So we'll talk a little bit about that. All right, so I'll let you go ahead and read this this warning here, this tech tip, I should say. It's not a warning, it's a tech tip, and let you go through this on your own. Current shunts and amp probes. These allow for you to measure more amperage than your meter is usually allowed to. They'll put these inside of circuits for measuring current easier, things like that. We won't use a lot of these at KCC, but we will talk about it a little bit. All right, clamp on current probes. These are the way you're going to take that 10 amp circuit in your meter and actually be able to measure more current with your multimeter. So they make a amp clamp that goes with your multimeter. Then they just make a multimeter basically that is made for measuring amperage mostly, and that's this guy here. So we'll have a couple of these at the college that you'll be able to use. And this is for, if you want to clamp onto your alternator and measure your alternator. Most of the time you can't use the base multimeter to do that unless you have a clamp like this one. So we'll talk a little bit more about that. You'll get some experience with those. All right, measuring resistance. Resistance is measured with an ohm meter. So resistance is measured in ohms. If the ohm meter has a range setting set it to the highest range of unknown resistances, it is better to isolate the component from the rest of the circuit. If a negative resistance reading is obtained, look for a voltage on the circuit. So here's one of the things that you have to be careful with, with regards to your meter, is when you're measuring resistance, there can't be any voltage or current flowing. Okay, the circuit needs to be isolated. It needs to be open. So we oftentimes, when we're measuring resistance on what we like to call a leg of a circuit. So we're not measuring the whole circuit. We're not, maybe we've disconnected both the battery terminals and we're measuring, from one battery terminal to the other battery terminal, but we're not hooked up to the battery. Okay, so there can't be any voltage in the circuit while we're measuring. You can actually damage your meter and you won't get a good reading. So when we're measuring resistance, we're measuring in ohms with the power off. Okay. All right, differential pressure gauge. Now, I'm not going to get into this too much. I'm going to let you guys read through this. All right, measuring voltage and current in a series circuit. Okay, so here we have our meter leads, and then we're never going to really do this in real life. There's not going to be typically there's not going to be 2 meters hooked in. We're talking about $800 worth of meters here or something. So here we have our meter hooked up, and we have 6 amps. Okay, so 6 amps is flowing through this meter down to this point. Okay, that's got the circuit closed. And then we're measuring 12 volts right here. So that means that 12 volts with 6 amps are dropping across this 2 ohm resistor. Okay, and in this case we have all three. We have amperage, voltage, and resistance, so we don't need to find for anything. But if we had 2, we could find for the third. All right, increasing the ohms to 3 ohms instead of 2 in our last. We still have 12 volts, nothing's changed with our voltage, but now we have 3 ohms, and then that dropped us down to 4 amps. Okay, 4 amps of resistance. I'm sorry, 4 amps of current, I should say. All right, measuring voltage drops. So if you look here, from positive to negative, we have 12 volts of drop. Now they're measuring all the way around and back again. And so on these wires all the way around, that's 12 volts drop, and that's normal. Okay. Now between this point and this point, they're saying we have 4 volts of drop, and between this point and this point, between these two, between here, okay, between these two, or between right here, we have 8 volts of drop. Now there are some rules having to do with electricity, and one of the rules is that when you're measuring the whole circuit, whatever your source voltage, if you have a 12 volt battery, from here all the way around, we have to use up almost all the voltage. Okay, so that's the voltage drop. The sum of the voltage drops has to equal the source voltage. And we'll talk about those laws, and we'll recite them and pound them into your head. All right, series circuits have only one path for current flow. Okay, the sum of all of the voltage drops in a series circuit is equal to the source of the voltage. So we talked about that. The total circuit resistance is the sum of all of the resistance in the circuit. Now that's only true for series circuits, and we'll get into that a little bit more as we go through. We're gonna work on this concept for quite a while. All right, parallel circuits. The parallel circuits have different rules. Parallel circuits contain multiple paths for current to flow. Voltage drops in a parallel circuit always equal the source voltage. Okay, so that's the same. Voltage drops in a parallel circuit always equal the source voltage. Okay, so that's the same as series. The sum of the current flow in each branch of the parallel circuit is equal to the total current supplied by the voltage source. And so we'll talk a little bit about that. That's a little different. That's a little bit of a different concept. Adding additional parallel resistance decreases the total circuit resistance. So we'll talk a little bit about how this works. This is interesting. This is some automotive electrical trickery, sort of. As you're learning this, it seems very weird and seems very foreign, but once you get the concept, it's pretty normal, and you can figure it out. Total circuit resistance in a parallel circuit is always less than the smallest resistor. So these are some of the rules and laws. So we will refer back to these as we go through our labs. To calculate total resistance in a parallel circuit, use the product over the sum formula. So we'll talk about this. And this is way too early to get into some of these concepts, so don't get too crazy about it. We are going to ease into this. Okay. So when you come to lab, you will have read this chapter. You will not have understood most of it, and we will start to clarify these things in lab. We are just introducing the concepts at this point. Don't feel like you have to master the concepts. If you're a very good audio-visual learner, you will get it, but if you are not, it's no big deal. We are going to taste it, touch it, smell it. You'll get to that hands-on learning, and we will solidify these concepts, but we're just introducing them at this point. Don't freak out if you're not getting it. All right, I'm not going to go through this right this second. I'm going to glance over it. You can look at it, read it, see if you understand it. You probably won't understand it at this point in the class. We will go over this at the appropriate time. Read over this, kind of look at it, see if you can understand it. If you can't, it is no big deal. It is way too early for you to understand this. We haven't tasted it, touched it, smelled it, played with it, made it go on, made it go off. You're going to get this by the time it's said and done. Do not freak out at this point. All right, so metric prefixes. Most of you will have gone through or will be going through your math at this point. Okay, and so maybe right about this time you'll be going through your math. But we're going to be doing a lot of unit prefixes and moving decimals with regards to electricity. So get used to this concept. Mega is 1,000,000, kilo is 1,000, milli, or the small m, is 1,000th. So we move that decimal, over from here to there, so it's 1,000th. The micro, this backwards U looking, or I guess it's a forward U with a dangle, I don't know, whatever this bad boy is, this little micro symbol. We're going to get very used to this, and that is a millionth. 1 divided by 1,000,000, okay? 1 with 6 zeros, right? And then we have the nano, which is, again, really huge. I would have got like 9 zeros here. And then a pico. Nanos and picos we don't deal with much in automotive and diesel. You would if you were an electronics tech, because these are some of the very small measurements they use. All right, 3 resistors in parallel. Now, what I want you to notice here when they're measuring this, one of the rules for parallel resistance was that the resistance total would be smaller than the smallest resistor. So right when I look at this, I don't even have to look. If I covered up this multimeter over here, I could look at this and say, I know for a fact, for a mathematical certainty, that my resistance is going to be less than 10 ohms. And it is, it's 5.5 ohms. Okay, so I can figure that out very quickly, what I'm looking at as far as that goes. All right, I'm not going to read through the summary because this is such a long lesson, okay? Read through this, try to verify or solidify some of these concepts as you read through. If you're an audiovisual learner, this may be very good for you. If you're a hands-on person, read through this, glance through it. We're going to touch it, taste it, smell it, turn it on, turn it off, make it buzz, make it ding, make it do all sorts of weird stuff. And hopefully you'll get it at that point. But these PowerPoints are important. I do want you to go through them and try to listen, because these are the rules. Now, you may not get the rules all the time, so I'm going to quote the rules all the time as we're going through this process, okay? We're going to quote the rules. All right. Again, I'm not going to go through these. We'll talk about ohms, volts, resistance, current, amperage, all of these things in depth, and we'll talk more about it in lab. All right. I want you to make sure that you are doing these PowerPoints and that you are following through. This PowerPoint's about an hour long, so that was a long one. It could be that we'll do some like this. I know that this tip doesn't probably help you towards the end, but feel free to take breaks, play some Call of Duty, do whatever you got to do as you're going through this. All right, thank you very much.